Hi students, welcome to Inside Physics. Today we are going to discuss about semiconductors. What are semiconductor materials? See, a material which has conductivity far greater than the insulator and significantly lower than the conductor is called a semiconductor material. So, what actually a semiconductor material signifies is it has low conductivity, and in periodic table there are total 11 semiconductor materials are there in the fourth group of periodic table. In the fourth group. So, based on their conductivity and thereby resistivity, these materials are classified as semiconductors. So, here there are two types of semiconductors. One is elemental semiconductors, second one compound semiconductors. So, for an example for elemental semiconductor is germanium and silicon. An example for compound semiconductors are gallium arsenide, gallium arsenide and indium phosphide, indium phosphide. So these are the best examples for elemental and compound semiconductors. Elemental semiconductors are mostly used in semiconductor devices. Compound semiconductors are mostly used in optoelectronic devices such as lasers and LEDs. So here there is a thing here in semiconductors is directly a semiconductor material can be used in semiconductor devices. If we say that question, the answer is no, because the actual conductivity is not up to the mark, so that they are used in the optoelectronic devices and other semiconductor devices. So what we need to do, we need to increase the conductivity of the semiconductors. For that we use a method of called doping. Doping is a method with which we combine a semiconductor material with another material which is called an impurity, which is added to the semiconductor material to increase the conductivity. So what kind of materials can be added to the semiconductors to increase their conductivity by the method of doping? So as the semiconductors are fourth group elements in periodic table, so the atoms which are very similar, not exactly similar but almost similar to the fourth group elements are, we can say, the neighbor groups, third group and fifth group, and secondly we can also consider second group and sixth group. So the neighboring atoms which are almost similar to the fourth group semiconducting materials can be considered as third group and fifth group, second group and sixth group. This first preference and second preference. So these materials can be added as an impurity on very less percentage, so that they will become high conductive elements, so that they can be used in semiconductor devices. So for that purpose, based on the doping, we divided the semiconductors in two categories. First one, extrinsic semiconductors and intrinsic semiconductors. So if a semiconductor material is considered as a pure semiconductor when we doped with some element, already we have seen, with a impurity element like third group or fifth group element, that becomes an extrinsic semiconductor, which is an impure semiconductor. So it's lost its purity, and because we added some impurity to that semiconductor to increase the conductivity. So extrinsic semiconductors are very widely used in see the devices, electronic devices, semiconductor devices, so that the electronic industry is growing day by day, and the requirement of extrinsic semiconductors is also growing. Here, if you want to go into the details how the behavior of a semiconductor material will, we can understand the material behavior by applying the quantum mechanics to the material and its electron revolving in the materials and electron movement in the materials. So if you apply quantum mechanics, we can study the electron energy levels in the material, so that the electron energy levels of the electron will give the most of the properties of the material. So in 1928, Felix Bloch, a scientist, proposed zone theory, for to study the electron energy levels and their splitting in the solids. So this zone theory is popularly known as band theory of solids. Band theory of solids. So this band theory based on quantum mechanics will actually tell about the electron properties and thereby material properties. So by understanding everything about the energy levels and their splitting by band theory of solids, how the atoms are interacting and thereby how the electrons are creating energy levels and thereby band of energies. So thereby these understanding has created a great opportunity for minimizing the electronic devices, miniature of electronic devices and semiconductor devices. So the devices day by day are becoming very thin and very small. So this is how the semiconductor introduction can be understood. Now we move to band formation of in a solid, how the band formation, energy band formation is done. Energy band formation is done. So I already told you, because of quantum mechanics and its application to the material, to the electrons, it actually tells about the energy level and its formation of bands, and thereby when a number of more than one atom is interacting with the other atom, so it further splits, the energy is split into the energy levels. We see how it goes. Energy band formation. What is an energy? Suppose if we take one atom, so it has some energy level. We can say that the energy level is E, represented with E. So if in a material, if the atoms are far away, so the interaction between the atoms is negligible. They almost don't interact with each other. So if the interaction needs to be done, so atoms needs to come closer. The proximity of the atoms must be closer. So then what happens if n number of atoms are coming closer to each other? So there are energy levels with same energy E, and they form an energy equal to almost the same energy, and the level of n atoms interacting is also equal to the E, and it can be represented with Ne. Okay, so this can be illustrated by taking an example how the atoms will interact and how the proximity of the atoms will take a great part in the interaction of the atoms. Suppose, see, with for understanding this concept, we take the help of molecular orbital theory. So see, if an atom has an energy E and it is represented with some function psi a, which represents an atomic orbital. It represents an atomic orbital, Another atom is also having an energy E, and it is represented with the atomic orbital psi b. So an atomic orbital is a space where the electrons revolving around the nucleus will be exactly identified, and the probability density is very high at this orbital. This is called atomic orbital. If we say the energy is E1, Ea and Eb, then if two atoms are interacting, what happens? See, the interaction means if two atoms are coming close to each other, the nucleus of first atom will have an effect on the electrons by attracting the electrons of the second atom. At the same time, the two nuclei of two atoms will also have some repulsion effect. So thereby they have a combined effect of attraction and repulsion. In that case, see, the electrons not only after interaction, when the two atoms are interacting, we can say the electrons will revolve around the two nuclei, not around one nuclei. So they will, after coming closer with close proximity, suppose if we say the atomic distance is d, and the distance between two atoms is suppose r. Okay, if r is far greater than d, that means the distance between two atoms is far greater than the atomic distance, then there is no interaction, we can say. If r is equal to d, then we can say the atoms are having sufficient proximity to have an interaction. So in this case, if we have the two atoms have to interact, r must be equal to the atomic distance. The distance between two atoms must be equal to the atomic distance. So in this case, the electrons of two atoms will be revolving around the two nuclei. We will take an illustration, an example for this, and we will see how the atomic orbitals will be combining to have a molecular orbital to have the energy level understanding. If we say we can take the hydrogen atom, a single hydrogen atom H12. So if this hydrogen atom has electrons in 1s level, energy level, okay. So if the atoms of hydrogen are coming close, very close in proximity, and they are coming very close to form a hydrogen solid. If you take an example like this, then what happens? See, the electrons in 1s energy level will be interacting with a neighboring atom, and they will be forming two energy bands like bonding orbital and anti-bonding orbital. So we know that if, see, psi a is the atomic orbital of one hydrogen atom, and psi b is the another atomic orbital of another hydrogen atom. If they are coming and they are interacting very closely, so there can be a possibility of two orbitals, molecular orbitals. One is bonding orbital and one is anti-bonding orbital. This bonding orbital is represented with psi plus, and this anti-bonding orbital is represented with psi minus. Here there is nothing difficult to understand here. See, the space around which an atom is interacting will be doubled here, because an atomic orbital, when what happens when two atoms combine and to form a solid or liquid or gas, what happens? It takes a molecular structure. See, atoms combine to give a molecular structure. So in this case, See, psi plus is called bonding orbital, psi minus is called anti-bonding orbital. How they can be represented means, see, psi plus can be written as C1 psi A plus C2 psi B. The combination, see, anti-bonding orbital can be written as psi A minus C4 psi B. So this is the mathematical representation of bonding and anti-bonding orbitals, where C1 and C2, C3, C4 are constants. Psi A and psi B are atomic orbitals. Psi plus is bonding molecular orbit, psi minus is anti-bonding molecular orbital. See how they are represented with diagrams. If we can represent it with a diagram, we can understand it better. So I will draw an energy level diagram. Okay, and the atomic orbital which are interacting. Before interacting, we can write like this. This is psi A, this is psi B. So when a bonding orbital is formed, the same diagram will look like. So this is psi plus bonding orbital. So if we want to draw a diagram for anti-bonding orbital, this is the energy taken on this x-axis. See, this is psi, suppose is considered as psi A, and this will become psi B. So we can say this is psi minus, which is called anti-bonding orbital. So if you observe the energies of psi plus and psi minus, if you observe the energies, how they are either more than the individual atomic orbitals or less than the atomic orbitals. If you consider psi plus bonding orbital, see the energy of this one is far less than the energy of individual atomic energy level. So what happens when they combine, the two atoms combine and form a bonding orbital? See, this molecular orbital has a less energy than the individual energy of the atom. In the same way, this can be written as, if we want to write in the energy form, this can be written as E dash, and the energy of anti-bonding orbital is greater than the individual energy of the atoms. Okay, so the anti-bonding orbital is having a greater energy than the individual energy of the atoms. So in this way we can understand how a molecular orbital theory can explain the interaction of atoms. Okay, and thereby we can understand the energy bands and their splitting. Now we understood the energy, how the energy bands are formed. How the energy bands are formed? Again, I am repeating. See, a band is a group of energy levels. So energy level is a thing which is considered for the electron. So when the electrons are interacting with other neighboring electrons, they form a continuous energy levels. So the levels formed continuously like a ladder, steps in the ladder, they form a band. So in this way, energy band formation is done in the solids. So the energy level, each level will split according to the number of atoms interacting. Suppose, see, when there is no interaction, see, there is enough space, so they are not interacting with each other, the energy level of each atom is same. it is not splitting and they are not interacting, means each having their separate energy levels. Suppose two atoms are interacting, that means R is equal to D. See, D is nothing but atomic distance. Atomic distance is not considered as diameter of the atom, and it comes with the radius of the atom. Okay, so here two atoms interacting means each energy level of the atom is split into two levels. Okay, again the second energy of the atom is again split into two levels. Two atoms interacting and each energy level is split into two levels. Again, if you suppose there are three atoms interacting, there are three atoms interacting, each energy level will split into three parts. Here I am writing in this part, this is the first energy level of first atom, and it is, we can write this as E1 dash, E1 double dash, E1 triple dash. So this energy, see, this is split into two, split into three. Again the second energy level of the second atom, see, again it is split into three. E2 double dash, E2 triple dash. Again the third level will be split in the same way. So if n atoms are interacting in the same way, then each energy level will be splitting into n parts. So this is how this is called energy level splitting. So because of this energy level splitting only, we can identify the conduction properties of the materials. See, what we are doing here, because all studying with the band theory, means we need to understand the conduction properties of the semiconducting materials. And see, the conduction is almost, and its temperature coefficient with the conduction is almost, we can stabilize the conduction in some interval of temperature. Okay, so these are all the things we can understand with the energy band formation and thereby studying band theory. Okay, this is all for now. In the next lesson we will see some more topics in semiconductors. Thank you.